In this video we are going to prove one of the important theorems in group theory called Cayley's theorem. Okay, so let me write it down and I will prove it. It's an important theorem because it tells you something about structure of groups, and the proof is fairly easy given that we have understood already some facts about group actions. Okay, Cayley's theorem is the following. So let G be a finite group. Of order n. Let's say G is a finite group of order n, and that means G has exactly n elements. Then it says, then G is isomorphic to a subgroup of Sn. Okay, so it says simply this is the theorem. If G is a finite group of order n, G is isomorphic to a subgroup of Sn. Recall that Sn is the symmetric group on n letters. So I said this is a structural result about groups because symmetric groups are very general in this sense. Every group, finite group, can be put inside a symmetric group. So if you study symmetric groups and all their subgroups, you would have studied all groups. That is the point of Cayley's theorem. Every finite group is isomorphic to a subgroup of Sn, where n is the order of the group. So for the proof, we are going to consider the action of G on itself by left multiplication. Okay, so when I defined actions, group actions on a set S, I'll give you several examples. Two of those examples were group acting on itself. So the group is G, the set is also G in these examples. And there were two important actions that I highlighted at that point of a group on itself. One is by left multiplication, the other is by conjugation. Okay, so in this proof we are going to apply the action of G on itself by left multiplication. This means if you have G, so here the set is also G, because G acts on itself, and then G comma S is simply GS, which is the GS is simply the product of G and S in G, right? So this is the product inside the group G. So let's use this. Now how do I use this? So I'm going to fix a G in G. First fix a small g in G. Consider the function G to G. Because this function is dependent on G, let me call this phi sub G. Consider the function defined by, I'll take small s, phi G of S is GS. So remember, G is playing two avatars here. One is as a group, the other is as a set. Here I am thinking of G as a set. I am fixing a group element G. I am giving you a function on the set to itself. It's a function from the set G to the set G. Because it is determined by small g, I am going to denote the function by phi subscript G. So what does it do? It takes an element small s and maps it to GS. We claim that phi G is a bijection. Phi G is a bijection. See, certainly phi G is a well-defined function, right? It takes an S and maps it to GS. So there is no problem. Phi G is a well-defined function. Phi G is a well-defined function. Now let's take this function and we want to show it's a bijection. So in other words, we want to check it is 1 1 and it is on 2. So why is it 1 1? What is 1 1? 1 1 means if two things, so it is a function g to g, if S1 and S2 map to the same thing, then S1 and S2 must be equal. So let's say phi g of S1 equals phi g of S2. Suppose that happens. This implies, what is phi g of S1? That is GS1. What is phi g of S2? That is GS2. GS1 is equal to GS2. Remember, G is the element of capital G, S1 is also element of capital G, but S1 is being thought of as a set element of the set G. So I am using G, small g to denote group element, small s1, small s2 to denote the elements of capital G when it's being considered as a set. GS1 equals GS2, but this is a product in the group. That means S1 equals S2, the cancellation property in a group. So S1 is equal to S2. So phi g S1 equal to phi g S2 means if the two things go to the same thing, they are equal to each other. This shows that phi g is 1 1, right? Two distinct elements go to the same thing means they are equal. So now it remains only to show phi g is onto. Why is phi g onto? What is the meaning of being onto? So it means you give me any element of the target space, there exists something that maps to this, right? You are given this, there exists such an element. So now let me be given an element S in capital G. So which element maps to this? So then phi g of G inverse S. Let's consider G inverse S, right? If S is in G, G inverse S is also in G. So what is phi g of G inverse S? By definition, this is G times G inverse of S. By associativity, this is G inverse of S, which is S, right? So if you give me an arbitrary element S, G inverse S maps to this under phi g. So phi g is onto. So phi g is 1 1 and onto. So phi g is a bijection, right? So this is the claim we made. We claim that phi g is a bijection, which I proved. G has n elements, right? That is the hypothesis. The hypothesis is that G is a finite group of order n. That means it has exactly n elements. What is Sn? Sn, I said, is the symmetric group on n letters. So Sn is the group of bijections of this set, right? But really the fact that we are calling the elements 1 to n is not important. Sn is the group of bijections of a set with n elements. Right? Remember, Sn is the group of bijections of an n element set. For convenience, when working with symmetric groups, it's convenient to call the elements 1, 2, 3 up to n. But it need not be those. Sn is the group of bijections for any element, n element set. G is one such. G is an n element set. So Sn can be identified with bijections of G, because Sn is a group of bijections of any set with n elements and G is a set with n elements. I can naturally think of Sn as a group of bijections. So it cannot be identified with bijections of G. I should write can be identified with the group of bijections Okay, so if you wish, you can call the elements of G as 1, 2 up to n because it has n elements. You fix some order, take the first element, call it 1, second element is 2, right? That's what we are doing here. Sn can be thought of as bijections of G, but phi G is a bijection of G. So now we have a function let's call it capital phi from G to Sn. What does it do? It takes a G and sends it to phi G that I defined earlier. Remember what is phi G? For a fixed small g, phi G is the function from G to G which sends S to Gs, which I have checked is a bijection. So phi G we already checked. Phi G is a bijection of S of G. So phi G is in Sn. Because Sn is, for the purposes of this theorem, we are thinking of Sn as the group of bijections of G itself. So phi G being a bijection of G is an element of Sn. So I am sending G to phi G. Now phi, capital phi is a function from a group to another group. So now I claim that phi is a group homomorphism. Okay, so this is you have to be careful here. So what is the function phi? It sends an element to another function. The function sends an element to a function. That's what capital phi is doing, because Sn is really functions of G to G, and a small g under the function capital phi goes to the function small phi G. So capital phi is a function that takes an element of the group G and sends it to a function which is what we are calling by phi G. So I am now claiming that phi is a group homomorphism, that is capital phi of G1 G2 is equal to capital phi of G1 composed with capital phi of G2. Remember the composition on Sn, when Sn is being thought of as bijections of capital G, the binary operation there is the composition. So you take two elements of capital G, G1, G2, we want to first multiply them and apply phi, then phi of G1 as a function composed with phi of G2 will give you the answer. So this must be true for all. Okay, so let's check this. So now we are saying two functions are equal because capital phi of G1, G2 is a function. So we are saying that. Okay, so first let me say the left hand side LHS left hand side and the right hand side RHS are both functions, right? What are they really? They are functions from G to itself, to G, because they are both in Sn, which we are considering as all functions, all bijective functions from G to G. For the purpose of this theorem, Sn is all bijective functions from G to G. This we can do, right, because G has n elements. So this is valid. And now LHS and RHS in this equation are both functions from G to G. So in order to be equal, so we are saying that these two functions are equal. Identical as functions. When do we say two functions are equal? Two functions are equal if they agree on every element of the domain, which in this case is G. So let us choose an arbitrary S in G. Again, G here is really playing the role of a set. So I'm taking an element small s. Let's take an element s in G, see what LHS and RHS do to S. Okay, so let's do LHS. LHS is phi of G1, G2. That's a function from G to G, right? What does it do to S? What does it do to S? Phi of G1, G2, remember, is phi G1, G2, because phi as a function from G to Sn sends a small g to phi G. That is the function capital Phi. So phi of G1, G2 is phi of small phi of G1, G2, and then applied to S it is this. But what is this? Now small phi was defined way back in the beginning of the proof. Small phi G is Gs applied to S. So small phi G1, G2 of S is G1, G2 S. Okay, this is what LHS does to small s. Now what does RHS do? What is RHS? RHS is phi G1 circle phi G2. This composition applied to S. Composition of function says that this must be phi G1 applied to phi G2 applied to S. That is the definition of composition. But what is phi G2? Phi G2 is small phi G2, right? Small phi G2 is small, capital phi G2 is small phi sub G2. This is phi G2, G1 by the way here. Phi small phi G2 of S is by definition of small phi is G2S. But this is equal to phi G1 of G2S, and this is equal to G1 times G2S. Now are these two equal? Of course they are equal, because this is the associativity in the group. So LHS equal to RHS as functions. Remember we are working with an arbitrary S. So and LHS and RHS agree on that arbitrary S. So they are equal as functions. So this proves that capital Phi is a group homomorphism. Right? So this justifies that statement that capital Phi is a group homomorphism. Now I want to claim that it's not only a group homomorphism, it is an injective group homomorphism. So I want to say phi of G is 1 1, phi is 1 1. Earlier we showed small phi is 1 1, but remember now we are saying capital Phi is 1 1. Small phi was in fact 1 1 and on 2, and hence became an element of symmetric group. Now I am saying capital Phi is 1 1, it is generally not on 2, it's only 1 1. Why is it 1 1? Because it's a group homomorphism. Capital Phi is a group homomorphism, we checked already. It is enough to check what? A group homomorphism is 1 1 if and only if the kernel of capital Phi is the identity element of G. Remember, a group homomorphism is 1 1 if and only if its kernel is identity. So this is what I am going to check. So suppose, so clearly E belongs to kernel Phi. Remember, this requires no additional statement because this follows immediately from the fact that Phi is a group homomorphism. So it sends identity to identity. So we need to check the opposite inclusion. So suppose G belongs to kernel Phi. Kernel Phi is a subgroup of capital G. Let's take a small g in it. This means Phi of G, which is what? Small phi of G. Remember, capital Phi is defined to be capital phi of G is defined to be small phi of G, small phi sub G. So this is small g is in the kernel means its image is the identity element. Of Sn. What is the identity element of Sn? Sn is the group of bijections of G. It is identity element means it is the identity function. So phi G is the identity function. From G to G, right? Identity element of the symmetric group is the identity function. So phi G is the identity function. Hence, phi G of S equals S for all S in capital S. This is the conclusion of small g being the kernel of capital phi. But what is phi G of S? Phi GS is by definition GS. So GS is equal to S for all S in S, right? In fact, this is a very strong condition. GS equal to S, remember, implies GS S inverse equal to S inverse. This implies G equal to E. This is the cancellation property, right? We can cancel S, that's the point. So G equal to E. Isn't that what we wanted? We said that kernel is identity only. We started with an arbitrary small g in kernel phi and we concluded that it is equal to G. So capital phi is 1 1. Now let's take stock of where we are. So now situation is capital phi from G to Sn is a 1 1 group homomorphism. It's a 1 1 group homomorphism. Now recall a point that I made after proving the first isomorphism theorem. If you have a 1 1 group homomorphism or injective group homomorphism, G can be identified with a subgroup of Sn. So by the first isomorphism theorem, remember, first isomorphism theorem says that a group homomorphism, if you have G mod the kernel, is isomorphic to the image. So G is isomorphic. In this case, kernel is trivial, right? Because it's injective to the image. By the first isomorphism theorem, G is isomorphic to the image. But note that the image of phi, in general, image of a group homomorphism is always a subgroup of the target group. In this case, this is Sn. So image of phi is a subgroup of Sn and G is isomorphic to it. So this completes the proof of Cayley's theorem, right? We remember what was Cayley's theorem. So that was the beginning of this video. Cayley's theorem said that, Cayley's theorem says that if you have a finite group of order n, then it is isomorphic to a subgroup of Sn, which is exactly what we have just proved. G is isomorphic to the image of phi and image of phi is a subgroup of Sn. So G is isomorphic to a subgroup of Sn. So this is Cayley's theorem, and this is a structural statement, not always very useful, and the reason that it's not always very useful is because Sn is a very complicated group. Okay, so Sn, one thing that we've noticed in that video when we talked about Sn is the size of Sn keeps increasing, right, by larger and larger numbers, because S3 has order 6, S4 has order 24, S5 has order 120, S6 has order 720, and so on. So Sn is a very complicated group. So knowing that every group is a subgroup of Sn is not in practice very useful. However, it's a good structural statement. It says that every group can be thought of as a subgroup of Sn. So I'm going to remark here something that we have proved earlier. Recall that a cyclic group is isomorphic to a quotient right. So compare this statement, cyclic group is isomorphic to a quotient of the form. So here also we are relating an arbitrary cyclic group to a well-known group like Z. So how do we show this? We take the map from G to G, sending 1 to the generator of G. Because G is a cyclic group, this is onto, and kernel is always of the form nz for some n. For some n I should write here. So by the first isomorphism theorem, Z mod nz is isomorphic to G. So this is also a structural theorem. So we are relating an arbitrary cyclic group to something well known. Cayley's theorem does the same. It relates, in fact, now an arbitrary group, any group, right? Any finite group, not just a cyclic group. Any finite group is actually can be put inside Sn. Think of it like this. It is isomorphic to a subgroup of Sn. So that means you can put it inside Sn. But the reason why this is very useful, that cyclic groups are of the form Z mod nz, is that Z is a very simple group to understand. So Z mod nz is a very simple group, and to say that every cyclic group is of the form is very nice. Whereas Sn is a very complicated group. So knowing that every subgroup is a subgroup of Sn is not in general that useful. Okay. Nevertheless, this is an important theorem in group theory because it says that every group sits inside Sn. So in theory, you know that subgroups of Sn exhaust all finite groups, right? This is what it means. If you list all the subgroups of symmetric groups for all n, then you have listed all groups. And that's a strong theoretical statement, and it's sometimes useful to, if you work with an arbitrary group G, it's sometimes to give it a concrete shape, and you can do that by putting inside Sn. And we have, done a lot of analysis of Sn. It has a cycle decomposition. It has every element can be written as a product of disjoint cycles. Every element is a product of transpositions. There is even permutations, odd permutations. So now knowing that every group is isomorphic to a subgroup of Sn, you can really think of elements of G as cycles because G is sitting inside Sn. And as far as group theoretic properties are concerned, they are preserved under the isomorphism. So G can be replaced by whichever group it is isomorphic to, which is a subgroup of Sn, and work with whatever we know about Sn. So in some cases, it is a good result because it helps us give a concrete shape to an abstract group. And that is why Cayley's theorem is an important theorem in group theory. So let me stop the video here. In the next video, we will continue our study of group actions. Thank you.